All right, so on this page of notes, we're going to be looking at some examples dealing with two different types of formulas involving circles. First of all, we have the area of a sector, and we're going to talk about what a sector is in just a moment. And we're also going to be looking at the arc length corollary, and that's going to give us something to talk about with arc length versus arc measure. All right, so let's talk about what a sector is first. So I'm going to draw a circle over here, and I'm going to cheat to do it because, well, you've seen my circles. All right, so with that circle then, it's going to mark the center, and we're going to draw an angle in here. A sector is a portion of a circle bounded by two radii and an intercepted arc. So here I have a radius, there I have a radius, and this, of course, is the intercepted arc. So what we're looking for is the area of this portion of the circle. We know how to find the area of a full circle, that being a equals pi r squared. The area of the sector is going to be, of course, smaller than the area of the circle itself. And the area of the sector is based on the measure of this central angle. And you may recall that we said a central angle is any angle in a circle whose vertex is the center of the circle. And I'm going to be referring to that angle as theta. Theta is a Greek letter, kind of resembles a capital O, but theta is a central angle. Specifically, its measure. And we are looking at measures in degrees. These could be done in a different form of angle measurement, but we haven't studied that yet, so we're not going to be working with those at all. So with that in mind, we kind of think of it as a proportion, or a fraction is probably a better way to say that. The area of this circle is a fraction of the whole area here. Specifically, it is the fraction that is formed by taking theta, that value of that central angle, or the measure of that central angle, compared to 360. So for the area of a sector, the area is equal to theta over 360, tells us what fraction of the circle we want, times pi r squared. So it's a fraction of the area of a circle. So if I had, let's say theta is 90 degrees, then 90 over 360 is a quarter of a circle, so this would be a quarter of the area. So whatever value theta has, we simply substitute that and the length of the radius to determine the area of the sector. So in our example, find the area of the sector, round your answers to the nearest hundredth. So here we have a radius of 12 centimeters, and we have a central angle of 154 degrees. So the area in this case would be 154 out of 360 total. That's the fraction of the circle that we want, times pi r squared, and r is 12. Keep in mind that we're only squaring the 12, we're not squaring the pi. Now you should be able to type this into your calculator all at once. 154 over 360 times pi times r, or 12, squared. And we're told to round to the nearest hundredth, so we end up with an area of 193.52 centimeters squared in this case. And that takes care of how we find the area of a sector. All right, now let's talk about arc length. We have extensively talked about arc measure in this chapter, specifically saying that the measure of an arc is equal to the measure of its central angle, and that value was given in degrees throughout everything that we've done. What we're looking at here is something entirely different, which is arc length. So here again, let's start with a circle. And we'll use that circle as our point of reference in this case. All right, so there's my circle. Mark my center. Here's a point. There's a point. And I know in this case that there's a radius. Whoops, missed my dot. I'm going to move my dot. Got my hand in the way and couldn't see where I was going. All right, so there's my radius in each case. Now this arc, let's call it AB. That arc has some length, but it also has a measure. The measure of the arc, in this case the measure of arc AB, is equal to whatever the measure of angle theta is. So here again, we're going to refer to this central angle as theta, just as we did up above. So the measure of the arc is equal to theta. That's going to be in degrees. But what is the arc length? Because I'm not referring to arc measure here. I'm referring to arc length. The arc length, if I think about what length means, length is usually something that I measure in units of length, like centimeters or inches or feet or yards or etc., etc., etc. Here, this is measured in degrees, so that can't be a length. So what do I mean by length? Well, let's assume that for a moment that I had a piece of string, and I could take that piece of string and start it at point A and lay it perfectly on the circumference of that circle all the way around to point B. And then if I take that string and stretch it end to end, that I can measure the distance between those two ends, that would be the length of the arc. Another person might say, well, what if I tried to take a ruler and I try to line it up here at A and I just follow that curve ever so precisely? Well, neither that version with the ruler or laying a string exactly along the curve of the circumference is going to be all that easy. So instead, the arc length is related to the circumference of the circle. Now remember, the circumference of a circle, if I think about circumference, circumference is 2 times pi times r. The arc length, the length of this arc AB, arc length is referred to as S. So here our S value would be the length of this arc AB. Well, the portion of the circumference that this arc has and the portion of the 360 degrees of the circle that theta has have to be equal to one another. So our arc length corollary says those two fractions must be the same. Whatever fraction exists between theta, that central angle, and 360 degrees, the whole circle, theta is a fraction of the whole, then the arc length must be the same fraction of the circumference, 2 pi r. So here we're talking about theta out of the whole 360. Here we're talking about the length of S versus the whole circumference. But that those two fractions must represent the same fraction of a whole. So if I were to say this is a 90-degree angle, I know that means it's a quarter of the circle. That means this arc length must be a quarter of the circumference. But ultimately, theta compared to 360, that fraction, must be equal to the arc length compared to the circumference, whatever that fraction may be. So in our example, find the length of arc AB. So we're finding S here. Round your answers to the nearest hundredth. We see a central angle of 113 degrees and a radius of 27 centimeters. So in this case, theta compared to 360, 113 over 360 must be equal to the arc length S over the circumference, 2 pi r. So 2 times pi times 27. All right, so let's see if we can get S by itself. Well, I'm going to simplify that 2 times pi times 27. 2 times 27 is 54, so that's going to become 54 pi. Now, if I think about this like a division problem, 113 divided by 360 equals S divided by 54 pi. Then that means to get S by itself is as simple as multiplying both sides by 54 pi. Since s over 54 pi is a division problem, do the opposite and multiply. What you do to one side, you must do to the other. So we're going to multiply in that form as well. And now we just go to the calculator. So 54 pi times 113 over 360. And we get a value, in that case, of 53.25 if we round to the nearest hundredth. This is a length, so give it an appropriate label, in this case centimeters. And that takes care of finding the area of a sector and finding the length of an arc. You'll have to keep straight the difference between arc length and arc measure.